Hello, everyone. Thank you all for joining the PowerAmerica webinar today and listen to my presentation. Before I start, I wish you and your family members are safe and healthy. My name is Dongdong, currently an assistant professor at CPAS Virginia Tech. My research interests are the wide bandgap power semiconductor-based high-frequency power electronics circuit and component design, high-power converter for grid, renewable, and transportation applications. Today, I'd like to give you guys an overview of a project funded by PowerAmerica on the topic of high-density bidirectional DC-DC converter for battery charging applications. We like to provide not only the project work, but also some of the research results developed from the program. Battery-based energy storage system is a very hot topic and is becoming a very big market in the energy and transportation sectors. Especially the fast adoption of electric vehicles accelerate the technology development on the lithium-ion batteries so that the battery kilowatt per dollar power and energy density has been improved significantly, so the battery system is penetrating into utility energy storage, electric aircraft, ships, and behind-the-meter commercial and residential applications. Meanwhile, the battery charging system, in particular the high-power isolated DC-DC or AC-DC converters, gain a strong attention in the power electronics society. Power density and efficiency, as well as the bidirectional power flow capability, are the key design metrics. Meanwhile, the converters are moving from low voltage to high voltage, such as 800 volts or even 1000 volt class. There are many topology and variations in the isolated DC-DC space. The very popular solution for high-power unidirectional system are the phase-shift full bridge or half-bridge converter with different type of rectifier variations and the resonant type converter like LLC. For the bidirectional system, the dual-active bridge and the CLLC resonant converters are the corresponding two popular options. In today's presentation, we will focus on the CLLC resonant converter as it achieves a full range source switching for lower switching loss and simple power stage design, small circulating current or reactive current for lower conduction losses, lower current harmonics in the transformer, and lower EMI emissions. In terms of the converter solution, the first question is that, can we simply put a single stage CLC converter to interface the battery with a voltage variation? If you refer to the typical LLC converter design process for power supply, the popular one is the FHA-based gain curve design, as shown in the right-hand side. The equivalent circuit model is shown in the bottom. You can simply vary the operating frequency to adjust the voltage ratio delivered by this LLC converter. Definitely, the loading condition will drive the selection of the operating frequency. For large power range and the voltage range, we need to put a large high-frequency AC inductor and operate in a very wide frequency range. Let's put the design complexity of the variable frequency transformer aside. The big issue of the typical LLC design approach is that the FHA-based gain curve design is basically obtained by assuming a pure resistive load, RE, and this RE can represent the charging power. However, in the real battery system, battery behaves more like a voltage source rather than a pure resistor. So the gain curve will not predict very well with the real battery charging operation. To look at the behavior of the battery charging system using a single stage LLC or CLC converter, we build a circuit simulation with a 700 volts battery modeled by an ideal voltage source in series with a small resistance representing the internal battery resistivities. We vary the operating frequency around the resonant point, which is 500 kHz in this particular case. We like to see the converter output voltage and the current regulation in terms of the variable frequency control. We also change the battery internal resistance from 2.5 ohms all the way to 0.1 ohms, and like to see how the battery model can affect the CLC converter operations. Here are the results shown by the 3D plots. The vertical axis shows the battery side current representing the charging power level. The X and the Y axis are the normalized switching frequency and the converter output voltage, which is also the battery voltage. The first takeaway we can find is that the converter behaviors controlled by this variable frequency are very different under different battery internal resistance, which cannot be predicted by the FHA-based gain curve design process. The second takeaway is that if the battery has a smaller internal resistance, the charging power at the lower battery voltage can vary a lot. In this case, from 0 all the way to a couple hundred amps in the very smaller operating frequency range. It means the frequency control is very hard to design for the charging power regulation. Also, at the higher battery voltage range, the converter cannot deliver enough output current, even if you operate in a very large range of the switching frequency. So these behaviors are very nonlinear, and the role of this battery internal resistance will make this single-stage variable frequency control-based LLC converter very difficult to design and operate. In the long life operation, battery internal resistance can vary over time, making the control even more difficult. Although we can add a large DC inductor between the LLC converter and the battery to help stabilize the control stability from signal standpoint, the single-stage solution is deemed hard to design and adapt to different battery systems. As we just discussed, the single-stage CLLC converter with a variable frequency control is difficult to interface with a battery that has a small internal resistance. We need to explore other options. The straightforward option shown on the left-hand side is to stack a second-stage buck converter. The big benefit is that it offers a very large voltage regulation range from 0 to full DC link, and the control is simple by adjusting the duty cycle. However, all the power has to run through the buck converter, leading to lower efficiency. Also, this buck converter will create a large full power DC inductor and large EMI noises. Therefore, another option is to adopt the so-called partial power processing solution. In this case, we only build up a low voltage regulation stage with the output of VPP and connected in series with CLLC output VMP. In this way, we can let majority power PMP go through the single-stage CLLC converter, leading to higher efficiency. Only a small power PPP will pass through the two stages partial power branch, but the converter will be a low voltage design with a small DC inductor. The partial power branch voltage and power readings will be smaller if the battery voltage variation range is small. So this partial power design can be applied to the battery with a voltage variation less than 40% around the average value. For both solutions, the CLLC converter operates at a fixed frequency at the resonant point. No AC inductors are needed and almost zero circulating current. This will make the transformer very small and efficient. We just said if the battery voltage variation is less than 40% or smaller, the partial power solution can offer better efficiency, density, and cost benefits. Fortunately, many battery system applications fit this condition. This page shows three examples. The first one is the Tesla Model S battery pack. Its voltage range is from 315 volts to 400 volts. The second case is the home battery system for residential and commercial applications. The voltage range is from 350 to 450 volts. The third example is the utility energy storage racks, and the voltage range is from 714 to 1000 volts. In all cases, the battery variation is less than plus minus 15% around the average value. This indicates a strong benefit of using the partial power solution. Later, we will show you a design example of partial power solution for 18 kilowatts battery system. There are two ways to control the CLLC resonant converter. The first way, and also a traditional way, is to operate it as an LLC converter. Therefore, the receiving side is treated as ISR rectifiers. It's simple, but actual DCD circuit is needed, and it's hard to operate at the bidirectional mode, as the control needs to swap the gating functions when power flips the direction. Another way to control the CLLC converter is to apply exactly the same signals on two sides. We name it as the dual-active synchronization control method. Such method is very simple, and no additional sensors are needed and can operate under bidirectional condition naturally. However, the ZVS soft switching of all switches are not the same as LLC converter. So the question here is, how can we maintain ZVS on all switches and various power conditions? So this page shows a simplified CLLC resonant converter. We replace the high-frequency transformer by three inductors. They are the magnetizing inductor in the middle and two leakage inductors on two sides. And on the right-hand side, it shows the key waveforms in one switching period.
The top waveform is the voltage measured across the device drain source terminal, and the bottom one shows the three currents measured on the three inductors. So during the T0 to T1 period, most of the power is transferred from sending to the receiving side. And from T1 to T2, that's the short daytime period, we want to make all the device finish the voltage transition and achieve the ZVS. Ideally, we like ZVS happen on all switches on both sides. The voltage transition during the daytime is mostly driven by the three current shown in the bottom. So now let me show you two non-ideal voltage transition results during the daytime. At the very beginning of the daytime, if assume two currents that flow through the leakage inductors share the same direction and is from the left-hand side to the right-hand side. According to the device voltage transition operation principle in a phase lag, the left-hand side two devices will start a voltage transition immediately as the current is flowing out of the phase lag. However, at that moment, because the right-hand side current is flowing into the phase lag, the device will be clamped by the anti-parallel body diodes and cannot start the voltage transition process. Then daytime losses are created on that phase lag until the right-hand side current flips the direction at the TA moment. Then let me show you another example. If two leakage currents now flows from the right-hand side to the left-hand side, then the right-hand side devices can start a voltage transition at the very beginning of the daytime, but the left-hand side devices will be clamped by the body diodes, therefore daytime losses are created. This operation stops until the left-hand side current flips the direction at the TA moment. So both cases are now considered as the optimal voltage transition operations. The conclusion here is, at the beginning of the daytime, if the currents on both sides of the transformer are in the same direction, either positive or negative, you will now achieve the optimal device voltage transition because additional daytime losses are generated. In addition, it potentially can create partial ZVS that produce more switching losses and EMI issues. Also, large current readings might happen during the daytime. So with the previous discussion, we learned that if we want to minimize the daytime loss, we have to start device voltage transition at the same time on both sides. Therefore, we need to meet the first design criteria. At the very beginning of the daytime, the currents on two sides of the leakage inductors have to be in the opposite direction, and both have to flow into the magnetizing inductor. With that, we can start the device voltage transition at the same time without additional daytime loss. Then, to achieve the optimal switch voltage transition, we have to make the devices on two sides finish the transition process at the same time at T2 moment. Otherwise, additional daytime losses will be created toward the end of the daytime. To achieve this goal during the entire daytime period, the ratio of the total discharge energies delivered by the two leakage inductors should follow the ratio of the device output capacitance from two sides. Then, it comes with the second design criteria. By meeting these two design criteria, it will make the device start and finish the voltage transition at the same time, thereby achieving the optimal voltage transition process and the ZVS for all the switching devices. However, the key point that I want to mention here is this design process has to be tuned at the full load condition rather than the light load case, because at the full load, the current that flows on both sides of the leakage inductors during the daytime can reach the maximum level. This large current can change the current direction on both sides. So the switching frequency and daytime need to be tuned at the full load condition in order to achieve ZVS over the entire power range. This is very different from the traditional LLC converter design, as the energy that is used to discharge the switch output capacitance is from the magnetizing inductor, regardless of the power level. However, in the CLLC converter, the ZVS operation is determined by the leakage inductor current, which is highly related to the power level. Due to the limited time, I cannot dive into the details of the optimal device voltage transition discussion, like showing the detailed circuit analysis, models, and equations. So here I just like to show you the high-level simulation and experimental results comparison between the non-optimal and optimal device voltage transition performance. On the left-hand side, it shows the bad design. You can see the device voltage on the bottom, that the devices on two sides didn't start and finish the voltage transition at the same time. Therefore, additional daytime losses are created. The current also shows large readings during the daytime period. In addition, there are high-frequency voltage readings created on top of the devices, leading to high EMI noises and voltage stress. However, on the right-hand side, it shows the optimal device voltage transition performance during the daytime. Both devices on two sides start and finish the process at the same moments. Therefore, no daytime losses are generated. The minimum voltage second is applied to the transformer leakage inductors during the daytime, leading to small current readings. ZVS are achieved on all the devices with very small voltage readings.
Now I'd like to show a 18 kilowatt battery charger system using the partial power solution. This is a project funded by PowerAmerica and the budget period 5 series. The industry collaborator is UTRC and Carrier. The application is for hybrid electric propulsion system or all-electric transportation refrigeration unit. The specifications are shown on the right. The power rating is 18 kilowatts. We chose 500 kilohertz to explore the high-frequency transformer design boundaries and limitations. The battery range is from 314 volts to 450 volts, with 375 volts to be the average value. The input voltage is fixed at 750 volts. The proposed solution contains two DC transformers. They are the high voltage DCX and the low voltage DCS shown in the blue. And the one regulator is behind the low voltage DCS shown in the yellow. The core concept of the partial power processing is pushing majority power through the single stage high voltage DCX, and only the partial power will go through the low voltage DCS, which is actually the CLLC converter, to regulate the output voltage and control the power flow. There are four candidates for DC regulator in the low voltage partial power branch: buck converter on the top left, full bridge on the top right, multi-phase interleaved buck on the lower left, and flank capacitor 3-level DC-DC converter on the lower right. Buck converter can be seen as a benchmark because other candidates have 4 devices, so to be fair, 2 devices are parallel in the buck converter. Compared with the buck, full bridge can provide negative output, so it can reduce the partial power branch voltage requirement by half, which means a lower voltage device can be selected. As for the flank capacitor converter, low voltage device also can be used because device voltage rating in the flank capacitor converter is half compared with the buck. As for the buck or multi-phase interleaved buck, higher voltage devices should be used. Among these candidates, buck, multi-phase buck, or flank capacitor can only provide positive voltage, but the full bridge can provide negative output voltage range. Therefore, the topology selection will also influence the turn ratio in the transformer design. As shown on the top left, the input voltage is a constant at 750 volts, and 2 design cases are shown on the right. A full bridge is adopted as a DC-DC regulator. VDCMV and VDCLV can be set as 375 volts and 75 volts. The corresponding turns ratio of the transformer can be determined. If the multi-phase interleaved buck or flank capacitor is adopted, VDCMV and the VDCLV should be set as 300 volts and 150 volts because these topologies can only provide a positive output voltage. Regulator loss at the full power with different topologies is shown on the bottom left. Around the battery nominal voltage, full bridge has the lowest losses because it can reduce the partial power branch voltage rating to 75 volts, leading to smaller switching losses. Also close to zero power delivered via the partial power branch around the nominal battery voltage. On the top right shows the RMS current which goes through the LV partial power branch transformer at the full power condition. Full bridge-based regulator has the lowest RMS current, which means the losses on the transformer in the low voltage partial power branch will be also reduced. The bottom right shows the power distribution between the partial power branch over the entire power delivered from the input to the battery. In average, full bridge also shows the smallest partial power over the entire voltage operation range. Therefore, the bottom left shows the total loss from the entire partial power branch at the full power condition. Full bridge regulator in average shows the lowest losses, leading to the best design option. Thus, the turn ratio has been selected to 10 to 5 and 10 to 1 for both the major power branch and the partial power branch. According to the discussion, the full bridge converter with 75 volts DC link is chosen as a partial power branch regulator. To further simplify the system, the full bridge with asymmetrical operation is adopted here. The converter has one leg operating in a high switching frequency for regulation purpose. In this case, is the S3 and S4 switches, and another leg, for instance, the S1 and S2 switches, is used to change the output polarity. To improve the efficiency further, the switching lag can be built by parallel interleaving. The regulator loss with different phase numbers is shown on the bottom left. Considering the trade-off between efficiency and power density, three-phase interleaving is selected. For the lag used for polarity switch, S1 and S2 can be changed to just the ultra-low RDS-on silicon MOSFET because their speed are very slow, so basically these two switches operate like a relay. Furthermore, each phase lag can be designed as a small module because the low voltage GaN device has been used, which will make the assembling easier. This page shows the final converter design and device selection. On the input side, 1.2 kV silicon carbide MOSFETs are used to construct the sending side full bridges. Each switching position has two devices in parallel. To simplify the design, two non-magnetic coupled transformers are designed and built for the main power transfer path and the low voltage partial power transfer path. For the main power transfer path, the turn ratio of the transformer is 2 to 1, so that the output voltage is 375 volts, exactly half of the input. And the main power receiving side adopts the 650 volts gallium nitride FETs. To handle the large current, four devices are put in parallel. For the low voltage partial power branch, a small 10 to 1 transformer is built, delivering 75 volts to the receiving side, followed by the full bridge regulator. So the regulator can provide plus minus 75 volts, making the entire converter output running from 300 all the way to 450 volts. The low voltage regulator operates at 200 kHz with a three-phase interleaving as discussed before. This will make the DC inductor extremely small. Two CLLC converters operate at the fixed frequency 500 kHz, and the entire converter, including the cooling system, is designed to fit 1U profile standard. In terms of the PCB design, the receiving side on the main power transfer path is a key design focus, as it needs to handle a large AC 500 kHz current, and it needs to facilitate 16 GaN devices with a good current sharing and small thermal stress. To reduce the loop inductance and reduce the current crawling, a two-dimensional flux cancellation layout is proposed in the multi-layer PCB design. The top view of the layout is shown on the right, and each switching position has 4 GaN devices in parallel. This full bridge is composed of two half bridge HB1 and HB2, and their cross sections are shown on the left. If we start at the SWA, current will go up and then turn left into the high side of HB1 via the top and mid 3 layers. And then the current will enter the DC bus via the mid 1 and mid 4 layers. Next, current will come out from the DC minus and go into the lower side of the HB2 via the mid 1 and mid 4 layer. Finally, current will come out from the low side of the HB2 and go into the SWB via the mid 2 and the bottom layer. If you pay attention to the current direction between the adjacent layers, their directions are opposite at both X and Y directions. Therefore, this layout utilizes two-direction flux cancellation to significantly reduce the loop inductances. The real PCB board for the high voltage DCS part is also shown on the left. 4 GaN devices are paralleled for each switching position. Finally, the Q3D simulation result shows the AC loop inductance is controlled within 5 nanohenry, and the current sharing between different layers is good. This page shows the converter testing at the full rated power condition, which is 18 kilowatts. As the receiving side handles the large AC current, the thermal image on the receiving PCB boards with the GaN devices is displayed here
together with the steady-state operation waveform of the 500 kHz transformer and output voltages from the CLLC converters. The device's case temperature is controlled at 42 degrees C. Heatsink and fan won't exceed 40 degrees C. This shows excessive thermal design margin, indicating further heatsink size reduction opportunities. It should be noted that RDS of the GaN device is very sensitive with the temperature, so a good thermal performance can also improve the total efficiency.
The dynamic testing results under the 16 kilowatts condition is shown in these slides. The battery output voltage is shown in yellow, and the current that goes through the main power transfer path and the low voltage partial power transfer path are shown in green and red. As the duty cycle changed from 100% to 25%, the output voltage shown in yellow changed from 450 volts to 390 volts. And then the three detailed waveforms for the RMV, RLV are shown at the bottom. With higher output voltage, the current RMV keeps nearly constant to transfer the majority power, and the RLV will increase to transfer more partial power. The steady-state testing results are shown in this page. As shown on the left-hand side, the duty cycle from the partial power branch is around 0, so all the power is transferred from the input to output via the single-stage CLLC converter in the main power transfer path, and the output voltage is around 375 volts. As shown on the right-hand side, when the duty cycle changes to 50%, the output increases to 413 volts, and about 2 kilowatts power is transferred through the partial power branch. This page shows the steady-state testing results with 75% and 100% duty cycle provided by the partial power branch voltage regulator. The corresponding output voltages are 431 volts and 450 volts. In the test, a converter was tested up to 23 kilowatts peak power. The total power conversion efficiency is shown on the left-hand side in this page. When the output voltage is 375 volts, we reach the peak efficiency around 98.8% because all the power is transferred from input to output via the single-stage CLLC DC-DC converter. As the output voltage increases from 375 volts to 450 volts, the partial power becomes larger and causes lower efficiency. And then the loss breakdown with different output voltage at rated power is shown on the right-hand side. The total loss is divided into three main components. They are the losses from the main power transfer loop, losses from the partial power branch, and the loss from the transformers. Now let's switch the gear and talk about the high-frequency transformer design for this CLLC converter. A CLLC resonant converter is characterized by fixed unity gain, with its input and output voltage relationship only being controlled by the turns ratio of the transformer. In order to reduce the gain variation around the resonant frequency, it's important to have a large ratio between your magnetizing inductance and the leakage inductance. But since the magnetizing inductance must be set to a certain value to achieve the ZBS, the leakage inductance should be minimized. Minimizing leakage inductance also has the added benefit of reducing the amount of processed reactive power, increasing the converter efficiency. To reduce the leakage inductance, we use the technique called interleaving for winding arrangement to improve the flux coupling between the primary and the secondary side of the windings. We follow the typical electromagnetic design process for the transformer, sweeping cross-section area, turns ratio, and so forth, and sought the highest efficiency and highest power density design. One thing to note is that in our design process, we did favor designs with less core loss just because of the thermal challenges associated with the low surface area planar transformers. This page shows the transformer for the main power transfer path, of which the number of turns are 8 for the primary side and 4 for the secondary side. The same Litz wire are used for both sides to reach the best fitting factor. This 18 kilowatt transformer has a size profile similar to a deck of cards, achieving 99.6% efficiency. 770 nanohenry leakage inductance referred to the primary side. The winding structure is shown in the bottom right, 4 total interleaved layers with 2 parallel secondaries S1 and S2 to handle 56 amps 500 kHz AC current. As we parallel the 2 Litz wires S1 and S2 on the secondary to handle the current sharing issues become prominent when it comes to very high frequency operation. Any small leakage inductance difference between S1 and S2 will result in a large unbalanced current sharing or so-called circulating current. Obviously, when we apply the best interleaving structure to reduce the total leakage inductance, we suffer the current sharing issues due to the asymmetry of the parallel secondaries. In our design, we observed over 50% unbalanced current sharing. Some other methods in the literature to improve current sharing are bifilar winding, where parallel secondaries are twisted together, but doing so results in the total height of our winding bundle increasing, which not only impact our total height profile, but interfere with our air gap, which was specifically designed to achieve ZVS. So bifilar winding is not desirable. External balancing transformers have also been used in the literature, but that doesn't make sense to use in a high-density transformer design, since it's basically adding an external transformer, which compromises the power density. So if we want to improve current sharing, it comes at the expense of either power density, leakage inductance, or losses. For instance, as shown in the bottom, we make a change of the winding arrangement by putting the 2 secondary side winding on top and bottom layers. This results in a symmetrical arrangement and helps balance the current sharing, but the total leakage inductance is almost doubled compared to the original design. In order to improve current sharing without compromising on loss, leakage, or density, we proposed a new winding strategy for these wire transformers called Intra-Leaving. We call this Intra-Leaving because in our proposed winding structure, winding layers can be non-homogeneous, meaning that a layer of secondary can have all your secondary windings in it, as opposed to only one as in the original interleaving structure. Let's look at an example. Shown on the slide is our interleaved structure with homogeneous parallel secondary layers. S1 only has S1 winding, and S2 only has S2 winding. To improve current sharing, we transpose 2 turns of S1 and S2, resulting in the non-homogeneous structure shown on the right. By doing this, we can improve the symmetry of the secondary windings in relation to the primary side and greatly improve current sharing. On the far right of the screen, we are showing how the parallel windings are crossed in space to achieve this structure. Current sharing simulation results are shown on the bottom, with the old design with normal interleaving on the left-hand side and the new design with our intra-leaving on the right-hand side. Current sharing error was reduced from 50% to 5% with the new structure, which is a 10x reduction. Simulation results also show similar loss and leakage inductance between the interleaved and the intra-leaved structure. In summary, we show a new winding method for Litz wire called Interleaving, which improved current sharing without compromising on leakage or losses.
In addition to the insulation voltage, SOMO is another design challenge for high-frequency, high-power transformer design. Particularly, the SOMO challenge is more severe on the windings in the high-power applications as the winding carries high current. In this example, we are designing a 2-to-1 ratio 500 kHz 18 kW air-cooled transformer with 750 volts as the input voltage. If we fabricated the transformer by following the best interleaving electromagnetic design configuration, it can be found that the winding inner layer temperature can go beyond 180 C, which is over 50 degrees higher than the outer surface of the Litz wire bundles. This is due to the stagnated air pocket trapped inside the Litz wire. Such stagnated air creates a thermal insulation layer, which causes the overtemperature and even the thermal runaway problems on the windings. To address the Litz wire overtemperature issue, potting plus forced convection cooling can be considered as a cost-effective solution for the high-frequency transformer. Epoxy materials are popular for thermal spreading, It has the balanced thermal, curing, and viscosity properties compared with other options like thermal grease and elastomers. Epoxy can be mixed with inorganic filler or powder materials to boost the K value for better thermal performance, but it needs to check the change on the breakdown strength, viscosity change, and curing conditions. Therefore, this page shows a potted winding by using epoxy as the potting materials. The potting is only applied to the windings to simplify the potting process. As such, all the air can be pushed out of the Litz wire bundle. This page shows a thermal characterization of this potted Litz wire-based 500 kHz transformer running at 18 kW power. Thermocouples are embedded inside the transformer to measure the temperature. A 24-watt, 120 mm high-speed fan is put on the side to create a forced convection cooling condition. Due to the epoxy, the maximum winding temperature drops to 126 degrees, and the delta T between the inner layer and the surface of the winding is only about 20 C. So it shows a good thermal performance, but it needs a large fan on the side. In order to further optimize the cooling performance, we need to find a way to reduce the fan and optimize the airflow condition. In order to further improve the cooling performance, we can take a look at the airflow velocity around the winding surface and see if we fully utilize the airflow for heat transfer. As soon as the air hits the boundary of the winding, the air molecules near the object are disturbed and move around the winding. Aerodynamic forces are then generated between the air fluid and the object. The magnitude of these forces depend on the shape of the winding. The disturbed air molecules around the front surface of the winding will in turn slow down the flow just above them. This creates a thin layer of air fluid in which the velocity changes from free stream to zero. This layer is called the boundary layer. Within the boundary layer, the thermal transfer performance is little affected by the fan. Therefore, a good aero design will push the boundary layer very close to the surface of the winding to better exchange the heat flux from the winding to the airstream. The simulation result clearly shows a boundary layer formation in the design. Therefore, cooling duct with the tabulator design for better aerodynamic performance is very critical to improve the thermal performance. The goal here is to leverage all the airstream and mobilize the air molecules on the surface of winding as much as possible. The cooling duct design needs to consider overall layout, winding size, and positions in order to guide airstream. The tabulator plates on the inner surface of the cooling duct are used to break the boundary layer and push the airstream stick to the surface of the winding as much as possible. They also create a tubular airflow around the winding surface. With such design, multiple transformers can be put side by side with a good thermal performance. The detailed cooling duct and tabulator design are now shown here, but the simulation result shows that a large boundary layer is broken by the duct and tabulator. Therefore, all the air molecules blew by the fan can be leveraged to carry the heat flux. The simulation result shows much improved performance with smaller fan requirement. This page shows the 18 kW transformer with a 3D printed optimized cooling duct for winding cooling. There are over 10-degree temperature improvement compared with the results without the duct. The fan can be reduced from the previous 120 mm 24-watt fan to just a 40 mm 3-watt fans. In this prototype, two transformers are put side by side, and both are cooled effectively. The power density is over 560 watts per cubic inches, a big improvement compared with the commercial high-frequency transformer solution.
As a summary, this page shows the final converter prototype. The major components are labeled in the picture. The DC inductors are the surface mount type placed on the backside of the PCB boards. Due to the partial power processing solution, the DC inductors are very tiny and are almost negligible. The converter was tested up to 23 kilowatts peak power for a short period of time. For many automotive applications, if the water cooling can be applied, we expect even smaller size due to the cooling system size reduction, making this solution more appealing. We have seen several 650 volts, 750 volt class silicon carbide discrete MOSFETs, so it can be used on the low voltage battery side instead of the GaN device to consolidate the design for both input and output side. We believe there are still many optimization work to do to further drive the power density and efficiency. So we look forward to the future collaborations with industry partners. Finally, let me just take a minute to introduce you about CPAS and Virginia Tech. We are working on a lot of power conversion technologies, from devices to active and passive components and all the way to the system. We currently have 81 industry partners and members to access the CPAS IP portfolios and research outputs, including the work that I presented today. Last but not the least, I'd like to thank PowerAmerica and the team for the funding, partnership, and education support. Without it, we won't be able to assemble the team and put the work together. I also like to thank my colleague Rolando Burgos and the CPAS graduate and undergraduate students to work on the project. We also appreciate the teams from UTRC and Carrier for their industry collaboration and support during the project. Due to the time limit, many details cannot be discussed in this presentation, so I'll provide a list of publications here for your reference. Many detailed information from converter modeling control to converter design to transformer design, fabrication, and test can be found there. If you have any questions, you can also reach me by the email provided in this page. Thank you all for your attention today.